Chapter 1 Relations and Functions. The concept of the term relation in mathematics has been drawn from the meaning of relation in English language, according to which two objects or quantities are related if there is a recognizable connection or link between the two objects or quantities. Let A be the set of students of class 12 of a school and B be the set of students of class 11 of the same school. Then some of the examples of relations from A to B are: number 1, set of ordered pair AB belongs to A cross B such that A is brother of B. Number 2, set of ordered pair AB belongs to A cross B such that A is sister of B. Number 3, set of ordered pair AB belongs to A cross B such that age of A is greater than age of B. Number 4, set of ordered pair AB belongs to A cross B such that total marks obtained by A in the final examination is less than the total marks obtained by B in the final examination. Number 5, set of ordered pair AB belongs to A cross B such that A lives in the same locality as B. However, abstracting from this, we define mathematically a relation R from A to B as an arbitrary subset of A cross B. If ordered pair AB belongs to R, we say that A is related to B under the relation R and we write as ARB. In general, ordered pair AB belongs to R. We do not bother whether there is a recognizable connection or link between A and B. Functions are special kind of relations. Types of relations. We know that a relation in a set A is a subset of A cross A. Thus, the empty set phi and A cross A are two extreme relations. For illustration, consider a relation R in the set A is equal to 1, 2, 3, 4 given by R is equal to set of ordered pair AB such that A minus B is equal to 10. This is the empty set as no pair AB satisfies the condition A minus B is equal to 10. Similarly, R dash is equal to set of ordered pair AB such that modulus of A minus B is greater than or equal to 0 is the whole set A cross A. As all pairs AB in A cross A satisfy modulus of A minus B is greater than or equal to 0. These two extreme examples lead us to the following definitions. Definition 1. A relation R in a set A is called empty relation if no element of A is related to any element of A. That is, R is equal to phi is a subset of A cross A. Definition 2. A relation R in a set A is called universal relation if each element of A is related to every element of A. That is, R is equal to A cross A. Both the empty relation and the universal relation are sometimes called trivial relations. Example 1. Let A be the set of all students of a boys' school. Show that the relation R in A given by R is equal to set of ordered pair AB such that A is sister of B is the empty relation and R dash is equal to set of ordered pair A, B such that the difference between heights of A and B is less than 3 meters is the universal relation. Solution. Since the school is boys' school, no student of the school can be sister of any student of the school. Hence, R is equal to 5, showing that R is the empty relation. It is also obvious that the difference between heights of any two students of the school has to be less than 3 meters. This shows that R dash is equal to A cross A is the universal relation. Two ways of representing a relation, namely roster method and set builder method. However, a relation R in the set 1, 2, 3, 4 defined by R is equal to set of ordered pair AB such that B is equal to A plus 1 is also expressed as ARB if and only if B is equal to A plus 1 by many authors. We may also use this notation as and when convenient. If ordered pair AB belongs to R, we say that A is related to B and we denote it as ARB. One of the most important relation which plays a significant role in mathematics is an equivalence relation. To study equivalence relation, we first consider three types of relations, namely reflexive, symmetric, and transitive. Definition 3. A relation R in a set A is called number 1 reflexive. If ordered pair A belongs to R, for every A belongs to A. Number 2 symmetric. If ordered pair A1, A2 belongs to R, implies that ordered pair A2, A1 belongs to R for all A1, A2 belongs to A. Number 3 transitive. If ordered pair A1, A2 belongs to R and ordered pair A2, A3 belongs to R, implies that ordered pair A1, A3 belongs to R for all A1, A2, A3 belongs to A. Definition 4. A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric, and transitive. Example 2. Let T be the set of all triangles in a plane with R a relation in T given by R is equal to set of ordered pair T1, T2 such that T1 is congruent to T2. Show that R is an equivalence relation. Solution. R is reflexive since every triangle is congruent to itself. Further, ordered pair T1, T2 belongs to R, which implies that triangle T1 is congruent to triangle T2, which implies that triangle T2 is congruent to triangle T1, which implies that ordered pair T2, T1 belongs to R. Hence, R is symmetric. Moreover, ordered pair T1, T2, ordered pair T2, T3 belongs to R, which implies that triangle T1 is congruent to triangle T2 and triangle T2 is congruent to triangle T3, which implies that triangle T1 is congruent to triangle T3, which implies that ordered pair T1, T3 belongs to R. Therefore, R is an equivalence relation. Example 3. Let L be the set of all lines in a plane and R with the relation in L defined as R is equal to set of ordered pair L1, L2 such that L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. Solution: R is not reflexive as a line L1 cannot be perpendicular to itself. That is, ordered pair L1, L2 does not belong to R. R is symmetric as ordered pair L1, L2 belongs to R, which implies that line L1 is perpendicular to line L2, which implies that line L2 is perpendicular to line L1. Ordered pair L2, L1 belongs to R. Therefore, R is symmetric. Therefore, R is not transitive. Indeed, if line L1 is perpendicular to line L2 and line L2 is perpendicular to line L3, then line L1 can never be perpendicular to line L3. In fact, line L1 is parallel to line L3. That is, ordered pair L1, L2 belongs to R. Ordered pair L2, L3 belongs to R. But ordered pair L1, L3 does not belong to R. Thus, R is not transitive. Example 4. Show that the relation R in the set 1, 2, 3 given by R is equal to set of ordered pair 1, 1, ordered pair 2, 2, ordered pair 3, 3, ordered pair 1, 2, ordered pair 2, 3 is reflexive but neither symmetric nor transitive. Solution: R is reflexive since ordered pair 1, 1, ordered pair 2, 2 and ordered pair 3, 3 lie in R. Also, R is not symmetric as ordered pair 1, 2 belongs to R, but ordered pair 2, 1 does not belong to R. Similarly, R is not transitive as ordered pair 1, 2 belongs to R and ordered pair 2, 3 belongs to R, but ordered pair 1, 3 does not belong to R. Example 5. Show that the relation R in the set Z of integers given by R is equal to set of ordered pair A, B such that 2 divides A minus B is an equivalence relation. Solution: R is reflexive as 2 divides A minus A, that is 0 for all A belongs to Z. Further, if ordered pair A, B belongs to R, then 2 divides A minus B. Therefore, 2 divides B minus A. Hence, ordered pair B, A belongs to R, which shows that R is symmetric. Similarly, if ordered pair A, B belongs to R and ordered pair B, C belongs to R, then A minus B and B minus C are divisible by 2. Now, A minus C is equal to A minus B plus B minus C is even. So, A minus C is divisible by 2. This shows that R is transitive. Thus, R is an equivalence relation in Z. In example 5, note that all even integers are related to 0 as ordered pair 0 plus or minus 2, ordered pair 0 plus or minus 4, etc. lie in R, and no odd integer is related to 0 as ordered pair 0 plus or minus 1, ordered pair 0 plus or minus 3, etc. do not lie in R. Similarly, all odd integers are related to 1 and no even integer is related to 1. Therefore, the set E of all even integers and the set O of all odd integers are subsets of Z satisfying following conditions. Number 1. All elements of E are related to each other and all elements of O are related to each other. Number 2. No element of E is related to any element of O and vice versa. Number 3. E and O are disjoint and Z is equal to E union O. The subset E is called the equivalence class containing 0 and is denoted by 0. Similarly, O is the equivalence class containing 1 and is denoted by 1. Note that 0 is not equal to 1. 0 is equal to 2r and 1 is equal to 2r plus 1, where r belongs to Z. In fact, what we have seen above is true for an arbitrary equivalence relation R in a set X. Given an arbitrary equivalence relation R in an arbitrary set X, R divides X into mutually disjoint subsets AI called partisans or subdivisions of X satisfying number 1. All elements of AI are related to each other for all I. Number 2. No element of AI is related to any element of AJ, where I is not equal to J. Number 3. Union AJ is equal to X and AI intersection AJ is equal to phi, where I is not equal to J. The subsets AI are called equivalence classes. The interesting part of the situation is that we can go reverse also. For example, consider a subdivision of the set Z given by 3 mutually disjoint subsets A1, A2 and A3 whose union is Z with A1 is equal to set of X belongs to Z such that X is a multiple of 3 is equal to set of infinitive to minus 6, minus 3, 0, 3, 6 up to infinitive. A2 is equal to set of X belongs to Z such that X minus 1 is a multiple of 3 is equal to set of infinitive to minus 5, minus 2, 1, 4, 7 up to infinitive. A3 is equal to set of X belongs to Z such that X minus 2 is a multiple of 3 is equal to set of infinitive to minus 4, minus 1, 2, 5, 8 up to infinitive. Define a relation R in Z given by R is equal to set of ordered pair A, B such that 3 divides A minus B. Following the arguments similar to those used in example 5, we can show that R is an equivalence relation. Also, A1 coincides with the set of all integers in Z, which are related to 0. A2 coincides with the set of all integers which are related to 1. And A3 coincides with the set of all integers in Z which are related to 2. Thus, A1 is equal to 0, A2 is equal to 1 and A3 is equal to 2. In fact, A1 is equal to 3R, A2 is equal to 3R plus 1 and A3 is equal to 3R plus 2 for all R belongs to Z. Example 6. Let R be the relation defined in the set A is equal to 1, 2, 3, 4, 5 by R is equal to set of ordered pair A, B such that both A and B are either odd or even. Show that R is an equivalence relation. Further, show that all the elements of the subset 1, 3, 5 are related to each other and all the elements of the subset 2, 4 are related to each other, but no element of the subset 1, 3, 5 is related to any element of the subset 2, 4. Solution: given any element A in A, both A and A must be either odd or even, so that ordered pair A belongs to R. Further, ordered pair A, B belongs to R implies that both A and B must be either odd or even, implies that ordered pair B, A belongs to R. Similarly, ordered pair A, B belongs to R and ordered pair B, C belongs to R, implies that all elements A, B, C must be either even or odd simultaneously, implies that ordered pair A, C belongs to R. Hence, R is an equivalence relation. Further, all the elements of 1, 3, 5 are related to each other as all the elements of this subset are odd. Similarly, all the elements of the subset 2, 4 are related to each other as all of them are even. Also, no element of the subset 1, 3, 5 can be related to any element of 2, 4. As elements of 1, 3, 5 are odd while elements of 2, 4 are even. Types of functions. Consider the functions f1, f2, f3 and f4 given by the following diagrams. In figure, we observe that the images of distinct elements of x1 under the function f1 are distinct, but the image of two distinct elements 1 and 2 of x1 under f2 is same, namely b. Further, there are some elements like e and f in x2 which are not images of any element of x1 under f1, while all elements of x3 are images of some elements of x1 under f3. The above observations lead to the following definitions. Definition 5. A function f from x to y is defined to be 1, 1 or injective if the images of distinct elements of x under f are distinct. That is, for every x1, x2 belongs to x. F of x1 is equal to f of x2 implies x1 is equal to x2. Otherwise, f is called many one. The function f1 and f4 in figure 1 and 4 are 1, 1 and the function f2 and f3 in figure 2 and 3 are many one. Definition 6. A function f from x to y is said to be onto or surjective if every element of y is the image of some element of x under f. That is, for every y belongs to y, there exists an element x in x such that f of x is equal to y. The function f3 and f4 in figure 3, 4 are onto and the function f1 in figure 1 is not onto, as elements e, f in x2 are not the image of any element in x1 under f1. Remark, f from x to y is onto if and only if range of f is equal to y. Definition 7. A function f from x to y is said to be 1, 1 and onto or bijective if f is both 1, 1 and onto. The function f4 in figure 4 is 1, 1 and onto. Example 1. Let A be the set of all 50 students of class 10 in a school. Let f from a to n be function defined by f of x is equal to roll number of the student x. Show that f is 1, 1 but not onto. Solution. No two different students of the class can have same roll number. Therefore, f must be 1, 1. We can assume without any loss of generality that roll numbers of students are from 1 to 50. This implies that 51 in n is not roll number of any student of the class, so that 51 cannot be image of any element of x under f. Hence, f is not onto. Example 2. Check the injectivity and surjectivity of the function f from z to z given by f of x is equal to x square. Solution. It is seen that f of minus 1 is equal to 1 and f of 1 is equal to 1. But minus 1 is not equal to 1. Therefore, f is many one function. Now, Rf is equal to set of 0, 1, 4, 9 up to infinitive is not equal to z, codomain. Therefore, f is not onto function. Hence, f is many one but not onto function. Example 3. Show that the function f from n to n given by f of 1 is equal to f of 2 is equal to 1 and f of x is equal to x minus 1. For every x is greater than 2 is onto but not 1, 1. Solution. F is not 1, 1 as f of 1 is equal to f of 2 is equal to 1. But f is onto as given any y belongs to n where y is not equal to 1. We can choose x as y plus 1 such that f of y plus 1 is equal to y plus 1 minus 1 is equal to y. Note, y belongs to n, y is equal to 1 implies that y is greater than 1 implies that y plus 1 is greater than 2. Also for 1 belongs to n, we have f of 1 is equal to 1. Example 4. Let f from n to n be defined by f of n is equal to n upon 2 if n is even, n plus 1 upon 2 if n is odd. Solution 1. For 1, 1, f is equal to set of ordered pair 1, 1, ordered pair 2, 1, ordered pair 3, 2, ordered pair 4, 2, ordered pair 5, 3 up to infinitive. Here, for 1 belongs to n, region. F of 1 is equal to 1 plus 1 upon 2 is equal to 1 because of 1 is unpaired. And for 2 belongs to n, region, f of 2 is equal to 2 upon 2 is equal to 1 because of 2 is paired. Hence, 1 is not equal to 2. But f of 1 is equal to f of 2 is equal to 1. F is not 1, 1 function. Number 2. For onto. Also for each n belongs to n, codomain. To n belongs to n, domain, so that f of 2n is equal to 2n upon 2 is equal to n. Because of since n belongs to n is a pair of 2n. Therefore, f is onto function. Composition of functions and invertible function. Consider the set A of all students who appeared in class 10 of a board examination in 2006. Each student appearing in the board examination is assigned a roll number by the board, which is written by the students in the answer script at the time of examination. In order to have confidentiality, the board arranges to deface the roll numbers of students in the answer scripts and assigns a fake code number to each roll number. Let B is a subset of N with the set of all roll numbers and C is a subset of N with the set of all code numbers. This gives rise to two functions f from A to B and g from B to C, given by f of A is equal to the roll number assigned to the student A and g of B is equal to the code number assigned to the roll number B. In this process, each student is assigned a roll number through the function f and each roll number is assigned a code number through the function g. Thus, by the combination of these two functions, each student is eventually attached a code number. This leads to the following definition. Definition 8. Let f from A to B and g from B to C be two functions. Then the composition of f and g, denoted by GOF, is defined as the function GOF from A to C given by GOF of x is equal to g of f of x for all x belongs to A. Example 1. Let f from set of 1, 3, 4 to set of 1, 2, 5 and g from set of 1, 2, 5 to set of 1, 3 be functions defined as f is equal to set of ordered pair 1, 2, ordered pair 3, 5, ordered pair 4, 1 and g is equal to set of ordered pair 1, 2, ordered pair 2, 3, ordered pair 5, 1. Find GOF. Solution. F from set of 1, 3, 4 to set of 1, 2, 5. F is equal to set of ordered pair 1, 2, ordered pair 3, 5, ordered pair 4, 1. F of 1 is equal to 2, F of 3 is equal to 5, F of 4 is equal to 1. G from set of 1, 2, 5 to set of 1, 3. G is equal to set of ordered pair 1, 2, ordered pair 2, 3, ordered pair 5, 1. G of 1 is equal to 3, G of 2 is equal to 3, G of 5 is equal to 1. GOF from set of 1, 3, 4 to set of 1, 3. GOF of 1 is equal to G of F of 1 is equal to G of 2 is equal to 3. GOF of 3 is equal to G of F of 3 is equal to G of 5 is equal to 1. GOF of 4 is equal to G of F of 4 is equal to G of 1 is equal to 3. Therefore, GOF from set of ordered pair 1, 3, ordered pair 3, 1, ordered pair 4, 3. Example 2. Find GOF and FOG. If F from R to R and G from R to R are given by f of x is equal to cos x and g of x is equal to 3x square. Show that GOF is not equal to FOG. Note, f of x is equal to g of x for all x belongs to A. Then f from A to B and g from a to b are equal function. Solution: we have GOF of x is equal to g of f of x is equal to g of cos x is equal to 3 cos x square is equal to 3 cos square x. Similarly, FOG of x is equal to f of g of x is equal to f of 3x square is equal to cos 3x square. Note that 3 cos square x is not equal to cos 3x square for x is equal to 0. Hence, GOF is not equal to FOG. Example 3. Show that if f from r minus 7 upon 5 to r minus 3 upon 5 is defined by f of x is equal to 3x plus 4 upon 5x minus 7 and g from r minus 3 upon 5 to r minus 7 upon 5 is defined by g of x is equal to 7x plus 4 upon 5x minus 3. Then FOG is equal to IA and GOF is equal to IB, where A is equal to r minus 3 upon 5, B is equal to r minus 7 upon 5, IA of x is equal to x for all x belongs to A, IB of x is equal to x for all x belongs to B, is called identity functions on sets A and B respectively. Solution: here we have GOF of x is equal to g of 3x plus 4 upon 5x minus 7 is equal to 7 into 3x plus 4 upon 5x minus 7 plus 4 upon 5 into 3x plus 4 upon 5x minus 7 minus 3 is equal to 21x plus 28 plus 20x minus 28 upon 15x plus 20 minus 15x plus 21 is equal to 41x upon 41 is equal to x. Similarly, FOG of x is equal to f of 7x plus 4 upon 5x minus 3 is equal to 3 into 7x plus 4 upon 5x minus 3 plus 4 upon 5 into 7x plus 4 upon 5x minus 3 minus 7 is equal to 21x plus 12 plus 20x minus 12 upon 35x plus 20 minus 35x plus 21 is equal to 41x upon 41 is equal to x. GOF of x is equal to x for all x belongs to B and FOG of x is equal to x for all x belongs to A, which implies that GOF is equal to IB and FOG is equal to IA. Example 4. Show that if f from A to B and g from B to C are 1, 1, then GOF from A to C is also 1, 1. Solution: suppose that GOF of x1 is equal to GOF of x2, where x1, x2 belongs to A, implies that G of f of x1 is equal to G of f of x2, implies that f of x1 is equal to f of x2 because G is 1, 1, implies that x1 is equal to x2 because f is 1, 1. Hence, GOF is 1, 1. Example 5. State with reason whether following functions have inverse. Number 1. F from set of 1, 2, 3, 4 to set of 10. F is set of ordered pair 1, 10, ordered pair 2, 10, ordered pair 3, 10, ordered pair 4, 10. Here f of 1 is equal to 10, f of 2 is equal to 10, f of 3 is equal to 10, f of 4 is equal to 10. Therefore, f is not 1-1 function. Therefore, f has not inverse function. Number 2. G from set of 5, 6, 7, 8 to set of 1, 2, 3, 4. G is set of ordered pair 5, 4, ordered pair 6, 3, ordered pair 7, 4, ordered pair 8, 2. Here G of 5 is equal to 4, G of 6 is equal to 3, G of 7 is equal to 4, G of 8 is equal to 2. Now G of 5 is equal to G of 7 is equal to 4. G is not 1-1 function. Therefore, G has not inverse function. It can be verified in general that GOF is 1-1 implies that F is 1-1. Similarly, GOF is onto implies that G is onto. Now, we would like to have close look at the functions f and g described in the beginning of this section in reference to a board examination. Each student appearing in class 10 examination of the board is assigned a roll number under the function f, and each roll number is assigned a code number under G. After the answer scripts are examined, examiner enters the mark against each code number in a mark book and submits to the office of the board. The board officials decode by assigning roll number back to each code number through a process reverse to G, and thus mark gets attached to roll number rather than code number. Further, the process reverse to F assigns a roll number to the student having that roll number. This helps in assigning mark to the student scoring that mark. We observe that while composing F and G to get GOF, first F and then G was applied, while in the reverse process of the composite GOF, first the reverse process of G is applied and then the reverse process of F. Example 5. Let F from set of 1, 2, 3 to set of A, B, C be 1-1 and onto function given by f of 1 is equal to A, f of 2 is equal to B and f of 3 is equal to C. Show that there exists a function g from set of A, B, C to set of 1, 2, 3 such that GOF is equal to IX and FOG is equal to IY, where X is equal to set of 1, 2, 3 and Y is equal to set of A, B, C. Solution: consider G from set of A, B, C to set of 1, 2, 3 as G of A is equal to 1, G of B is equal to 2 and G of C is equal to 3. It is easy to verify that the composite GOF is equal to IX is the identity function on X and the composite FOG is equal to IY is the identity function on Y. Remark: the interesting fact is that the result mentioned in the above example is true for an arbitrary 1-1 and onto function f from x to y. Not only this, even the converse is also true. That is, if f from x to y is a function such that there exists a function g from y to x such that GOF is equal to IX and FOG is equal to IY, then F must be 1, 1 and onto. Definition 9. A function f from x to y is defined to be invertible if there exists a function g from y to x such that GOF is equal to IX and FOG is equal to IY. The function g is called the inverse of f and is denoted by f inverse. Thus, if f is invertible, then f must be 1, 1 and onto, and conversely, if f is 1, 1 and onto, then f must be invertible. This fact significantly helps for proving a function f to be invertible by showing that f is 1, 1 and onto, especially when the actual inverse of f is not to be determined. Example 6. Consider f from R to R given by f of x is equal to 4x plus 3. Show that f is invertible. Find the inverse of f. Solution: f from R to R, f of x is equal to 4x plus 3. x1, x2 belongs to R. f of x1 is equal to f of x2, which implies that 4x1 plus 3 is equal to 4x2 plus 3, which implies that x1 is equal to x2. Therefore, f is 1, 1 function. Now, y belongs to Rf. Y is equal to f of x is equal to 4x plus 3, which implies that x is equal to y minus 3 upon 4. f of y minus 3 upon 4 is equal to 4 into y minus 3 upon 4 plus 3 is equal to y. Therefore, f is onto function. Therefore, the inverse of f exists. Therefore, the inverse of function f is f inverse of x is equal to x minus 3 upon 4. Example 7. Let f from n to R be a function defined as f of x is equal to 4x square plus 12x plus 15. Show that f from n to s, where s is the range of f, is invertible. Find the inverse of f. Solution: let y be an arbitrary element of range f. Then y is equal to 4x square plus 12x plus 15 for some x in n, which implies that y is equal to 2x plus 3 whole square plus 6. This gives x is equal to square root of y minus 6 minus 3 upon 2, as y is greater than or equal to 6, where x belongs to n. Let us define g from s to n by g of y is equal to square root of y minus 6 minus 3 upon 2. Now, GOF of x is equal to g of f of x is equal to g of 4x square plus 12x plus 15 is equal to g of 2x plus 3 whole square plus 6 is equal to square root of 2x plus 3 whole square plus 6 minus 3 upon 2 is equal to 2x plus 3 minus 3 upon 2 is equal to x. And FOG of y is equal to f of square root of y minus 6 minus 3 upon 2 is equal to 2 into square root of y minus 6 minus 3 upon 2 plus 3 whole square plus 6 is equal to square root of y minus 6 minus 3 plus 3 whole square plus 6 is equal to square root of y minus 6 whole square plus 6 is equal to y minus 6 plus 6 is equal to y. Hence, GOF is equal to IN and FOG is equal to IS. This implies that F is invertible with F inverse is equal to G. Example 8. Let F, G and H be function from R to R. Show that F plus G OH is equal to FOH plus GOH. F into G OH is equal to FOH into GOH. Solution: F, G and H are from R to R functions. Number 1. Left hand side is equal to F plus G OH is equal to F plus G into H of X is equal to F into H of X plus G into H of X is equal to FOH plus GOH is equal to right hand side. Number 2. Left hand side is equal to F into G OH is equal to F into G into H of X is equal to F into H of X into G into H of X is equal to FOH into GOH is equal to right hand side. Binary operations. Right from the school days, you must have come across 4 fundamental operations, namely addition, subtraction, multiplication and division. The main feature of these operations is that given any two numbers A and B, we associate another number A plus B or A minus B or A upon B or B is not equal to 0. It is to be noted that only two numbers can be added or multiplied at a time. When we need to add 3 numbers, we first add 2 numbers and the result is then added to the third number. Thus, addition, multiplication, subtraction and division are examples of binary operation, as binary means 2. If we want to have a general definition which can cover all these 4 operations, then the set of numbers is to be replaced by an arbitrary set X, and then general binary operation is nothing but association of any pair of elements A, B from X to another element of X. This gives rise to a general definition as follows. Definition 10. A binary operation star on a set A is a function star from A cross A to A. We denote star A comma B by A star B. Example 1. Show that addition, subtraction and multiplication are binary operations on R, but division is not a binary operation on R. Further, show that division is a binary operation on the set R star of non-zero real numbers. Solution. Addition from R cross R to R is given by A comma B to A plus B. Subtraction from R cross R to R is given by A comma B to A minus B. Multiplication from R cross R to R is given by A comma B to A B. Since addition, subtraction and multiplication are functions, they are binary operations on R. But division from R cross R to R given by A comma B to A upon B is not a function and hence not a binary operation. As for B is equal to 0, A upon B is not defined. However, division from R star cross R star to R star given by A comma B to A upon B is a function and hence a binary operation on R star. Example 2. Show that subtraction and division are not binary operations on N. Solution. Subtraction from N cross N to N given by A comma B to A minus B is not binary operation, as the image of 3, 5 under subtraction is 3 minus 5 is equal to minus 2 does not belongs to n. Similarly, division from n cross n to n given by a comma b to a divided by b is not a binary operation, as the image of 3, 5 under division is 3 divided by 5 is equal to 3 upon 5 does not belongs to n. Example 3. Let P be the set of all subsets of a given set X. Show that union from P cross P to P given by A comma B to A union B and intersection from P cross P to P given by A comma B to A intersection B are binary operations on the set P. Solution. Since the union operation, union carries each pair A comma B in P cross P to a unique element A union B in P. Union is binary operation on P. Similarly, the intersection operation intersection carries each pair A comma B in P cross P to a unique element A intersection B in P. Intersection is a binary operation on P. Example 4. Show that the V from R cross R to R given by AB to maximum A, B and the wedge from R cross R to R given by A, B to minimum A, B are binary operation. Solution. Since V carries each pair A, B in R cross R to a unique element, namely maximum of A and B lying in R, V is a binary operation. Using the similar argument, one can say that wedge is also a binary operation. Also, V A is equal to wedge A is equal to A. Remark. V 4, 7 is equal to 7. V 4 minus 7 is equal to 4. Wedge 4, 7 is equal to 4 and wedge 4 minus 7 is equal to minus 7. When number of elements in a set A is small, we can express a binary operation star on the set A through a table called the operation table for the operation star. For example, consider A is equal to set of 1, 2, 3. Then the operation V on A defined in example can be expressed by the following operation table. Here V 1, 3 is equal to 3. V 2, 3 is equal to 3. V 1, 2 is equal to 2. Here we are having 3 rows and 3 columns in the operation table with I, J, the entry of the table being maximum of ith and jth elements of the set A. This can be generalized for general operation star from A cross A to A if A is equal to set of A1, A2 up to AN. Then the operation table will be having n rows and n columns with ijth entry being AI star AJ. Conversely, given any operation table having n rows and n columns with each entry being an element of A is equal to set of A1, A2 up to AN, we can define a binary operation star from A cross A to A given by AI star AJ is equal to the entry in the ith row and jth column of the operation table. One may note that 3 and 4 can be added in any order and the result is same, that is 3 plus 4 is equal to 4 plus 3. But subtraction of 3 and 4 in different order give different results, that is 3 minus 4 is not equal to 4 minus 3. Similarly, in case of multiplication of 3 and 4, order is immaterial. But division of 3 and 4 in different order give different results. Thus, addition and multiplication of 3 and 4 are meaningful. But subtraction and division of 3 and 4 are meaningless. For subtraction and division, we have to write subtract 3 from 4, subtract 4 from 3, divide 3 by 4 or divide 4 by 3. This leads to the following definition. Definition 11. A binary operation star on the set X is called commutative if A star B is equal to B star A for every A, B belongs to X. Example 5. Show that addition from R cross R to R and multiplication from R cross R to R are commutative binary operations, but subtraction from R cross R to R and division from R star cross R star to R star are not commutative. Solution. Since A plus B is equal to B plus A and A cross B is equal to B cross A for all A, B belongs to R. Addition and multiplication are commutative binary operation. However, subtraction is not commutative since 3 minus 4 is not equal to 4 minus 3. Similarly, 3 divided by 4 is not equal to 4 divided by 3, shows that division is not commutative. Example 6. Star on Z plus A star B is equal to A minus B. Determine whether or not each of the definition of star given below gives a binary operation. Solution. Z plus is equal to set of 1, 2, 3, 4 up to infinity. A star B is equal to A minus B. Positive when A is greater than B. Negative when A is less than B. If A is equal to 2, B is equal to 5, then A, B belongs to Z plus. A star B is equal to 2 star 5 is equal to 2 minus 5 is equal to minus 3 does not belongs to Z plus. Therefore, star is not a binary operation on Z plus. Definition 12. A binary operation star from A cross A to A is said to be associative if in bracket A star B star C is equal to A star in bracket B star C for all A, B, C belongs to A. Example 7. Show that addition and multiplication are associative binary operation on R, but subtraction is not associative on R. Division is not associative on R star. Solution. Addition and multiplication are associative since in bracket A plus B plus C is equal to A plus in bracket B plus C and in bracket A cross B cross C is equal to A cross in bracket B cross C for all A, B, C belongs to R. However, subtraction and division are not associative as in bracket 8 minus 5 minus 3 is not equal to 8 minus in bracket 5 minus 3 and in bracket 8 divided by 5 divided by 3 is not equal to 8 divided by in bracket 5 divided by 3. Example 8. Show that star from R cross R to R given by A star B is equal to A plus 2B is not associative. Solution. The operation star is not associative since in bracket A star 5 star 3 is equal to in bracket 8 plus 10 star 3 is equal to in bracket 8 plus 10 plus 6 is equal to 24. While 8 star in bracket 5 star 3 is equal to 8 star in bracket 5 plus 6 is equal to 8 star 11 is equal to 8 plus 22 is equal to 30. Remark: associative property of a binary operation is very important in the sense that with this property of a binary operation, we can write A1 star A2 star up to star AN, which is not ambiguous. But in absence of this property, the expression A1 star A2 star up to star AN is ambiguous unless brackets are used. For the binary operation plus on R, the interesting feature of the number 0 is that A plus 0 is equal to A is equal to 0 plus A. That is, any number remains unaltered by adding 0. But in case of multiplication, the number 1 plays this role, as A cross 1 is equal to A is equal to 1 cross A for all A in R. This leads to the following definition. Definition 13. Given a binary operation star from A cross A to A, an element E belongs to A, if it exists, is called identity for the operation star if A star E is equal to A is equal to E star A for all A belongs to A. Example 9. Show that 0 is the identity for addition on R and 1 is the identity for multiplication on R, but there is no identity element for the operations subtraction from R cross R to R and division from R star cross R star to R star. Solution: A plus 0 is equal to 0 plus A is equal to A, and A cross 1 is equal to A is equal to 1 cross A for all A belongs to R, implies that 0 and 1 are identity elements for the operations addition and multiplication respectively. Further, there is no element E in R with A minus E is equal to E minus A for all A in R. Similarly, we cannot find any element E in R star such that A divided by E is equal to E divided by A for all A in R star. Hence, subtraction and division do not have identity element. Remark: 0 is identity for the addition operation on R, but it is not identity for the addition operation on N, as 0 does not belong to N. In fact, the addition operation on N does not have any identity. One further notice is that for the addition operation plus from R cross R to R, given any A belongs to R, there exists minus A in R such that A plus minus A is equal to 0. Identity for addition is equal to minus A plus A. Similarly, for the multiplication operation on R, given any A is not equal to 0 in R, we can choose 1 upon A in R such that A cross 1 upon A is equal to 1. Identity for multiplication is equal to 1 upon A cross A. This leads to the following definition. Definition 14. Given a binary operation star from A cross A to A with the identity element E in A, an element A belongs to A is said to be invertible with respect to the operation star if there exists an element B in A such that A star B is equal to E is equal to B star A, and B is called the inverse of A and is denoted by A inverse. Example 10. show that minus A is the inverse of A. For the addition operation plus on R and 1 upon A is the inverse of A is not equal to 0. For the multiplication operation cross on R. Solution as A plus minus A is equal to A minus A is equal to 0 and minus A plus A is equal to 0. Minus A is the inverse of A for addition. Similarly, for A is not equal to 0, A cross 1 upon A is equal to 1 is equal to 1 upon A cross A implies that 1 upon A is the inverse of A for multiplication.